This presentation covers of the operational side of manufacturing with the very important quality control laboratory function. It use of process flow charting and value stream mapping techniques and how they can be used in combination to produce integrated best practices. This includes a step-by-step walk through the mapping process. The idea of lean laboratory discussed in detail and how those concepts central to lean are applied to these types of quality control laboratories. Once again, value stream mapping is discussed but applied to the laboratory situation. Following on is a discussion of the integration of the lean laboratory with the manufacturing operations to generate a truly lean process. Layout, process operations, and performance measures are discussed and techniques referenced in it are given relevance in relation to real pharmaceutical situations. Electronic considerations are covered in terms of how they help to facilitate lean enterprising approaches to data handling and data management. The last part covers special considerations that need to be covered to avoid compliance pitfalls that would negatively impact on process implementation. Some key concepts that we will discuss along the way involve applying lean principles to laboratory practices using Kaizen continuous improvement, Kanbans, waste reduction, cycle time reduction, and process leveling. As in other areas of biopharmaceutical processes, the QC analytical laboratory must organize the workflow so that the results are processed and delivered with maximum efficiency. These are not the only considerations, however, because we want predictable regularity, acceptable processing costs, and the lowest risk of an operational mishap or mistake. Another requirement in support of manufacturing operations is that it can fully integrate with technical operations to provide timely release of the product in a compliant and controlled way into the marketplace and distribution network. In lean laboratory operation, the baseline tenets of lean are set in standardized and level flow, where oscillations from the operating norm are minimized to diminish inefficiencies at all levels. The use of the value stream mapping technique permits the identification of areas of non-added value, and this will become rich sources of opportunity for process improvement. Conversely, they will also identify where best practices are operating, and these can be replicated to be improve the overall process. For example, the process of data entry labeling might be very cumbersome using a combination of paper and electronic means to achieve the goal. They might also involve the analyst walking from computer station to a centralized printer across a hallway, for example, to print out labels or worksheets. In all these cases, there's a variety of waste sources, and these include motion waste, unnecessary repetitive data entry, over or under production of labels, and possible defect waste as mistakes are made. Therefore, when data is collected, collated, tabulated, and analyzed, there are additional areas of waste that become obvious opportunities for removal. In the new paradigm, the difference between lean laboratories and conventional laboratories will become enormous, specifically in terms of productivity, efficiency, and overall process effectiveness. The modern lean laboratory requires a paradigm shift in the way traditional laboratories have staffed, organized, and operated. With this shift comes operational flexibility, efficiency, and the potential for reduced running costs. And this is all achieved with the added bonus of better organization, integration with other functions connected with the supply chain performance, such as QA, manufacturing. In acknowledging this change in paradigm, a brief view of some key elements driving change is a worthwhile exercise. Note that this is not an all-inclusive list, but just some key interesting points that should be taken note of. The first of these is a lack of focus. There is often a lack of focus on the critical attributes associated with performing an analysis. Why is this? Frequently, there is a variable arrival time at the laboratory and a variable requirement for the type of analysis performed. This creates a variable load from a sample supply point of view and a variable processing time or cycle time for a given sample through the laboratory. Added to this, there is often little control over the journey of the sample once processing starts, because the emphasis is only on the accuracy of that sample or the individual test to make sure it's run efficiently. Often one finds that it takes as long as it takes. Clearly, there are multiple areas of waste associated with this type of operation, and efficiency is frequently sacrificed as a result. A second key point refers to long and variable lead times. Efficient testing runs cause a delay in the sample analysis, which results in queuing of samples and ultimately a backlog in the analysis process. This results in batching of samples for processing, which contributes to the long waiting periods between complete analysis runs. A third point is work prioritization fast-track mechanism. It's frequently the case that laboratories often attempt to be flexible to accommodate the need for an early release of a particular production lot or batch. This results in an even bigger headache for the smooth operation of the laboratory due to a disruption in the rate of flow of samples through the lab. Short-term prioritization of samples where known ground rules exist often cause inefficiency in the overall functionality, because the systems are always abused and sooner or later every sample is a priority number, which means nothing is a priority and a state of chaos results. Again, the various levels of waste increase and the objective or the intent of the program results in the opposite result. A fourth point is in relation to high levels of work in progress. Often QC laboratories are highly stressed work environments where a lot of samples require processing in a relatively short period of time. Frequently, this results in of high levels of work in process, or WIP, which result in efforts to label, track, and prioritize and assign work functions. In an attempt to solve this, sample analysis tools have been deployed, often with elaborate IT components, to address sampling. But these only seem to work until the next level of complexity is in, and then the same old issues raise their heads and waste and inefficiency increase. The solution is not to use IT tracking tools, but to re-engineer the whole approach to smooth flow. This will result in a stabilization of analysis and reduce the inherent waste from the system. Volatile workloads. Variability in the supply of samples within the QC laboratory, predicting capacity and requirements is often difficult. This inherent unpredictability frequently causes the problem. Peak moments of sample traffic and high productivity and suboptimal lead time performance are frequently followed by dramatic dips in performance with low productivity. As already mentioned, the key point here is to look at workload stabilization. This is done by clearly identifying which steps add value to the process and which do not. In doing this and mapping the results, each step of the process becomes a logical integrated step in the flow. Together with controlling the workload and mix of samples arriving, it is possible to level the workload and reduce or eliminate many non-added value elements which previously were a drag on the efficient system. Let's talk about causes of volatile workflow. Why is the flow not smooth? It's important to collect data which categorizes why something is occurring. For example, some areas of flow disruption include, but are not limited to, late stability pulls, input samples, end of shift priority requests, and emergency requests. It's important to categorize these because it's unlikely that they will ever disappear completely. So a complete and thorough analysis is necessary in order to build an appropriate approach to factor into the operating equation. Metrics also play an important role in the process by providing a mechanism to track performance. This is achieved by assigning performance indicators, or KPIs, to the process, and then using these to numerically monitor how well or how poorly the system runs. Efficiency and true improvements to the operation are made by revising these practices through the implementation of Kaizen strategies that are driven by performance metrics designed to chart progress. In the laboratory, waiting time is perhaps the single largest source of waste that can be identified and removed. But lean lab design is much more than just removing waste. Level flow plays a huge part in improving performance metrics in the lean laboratory. Through the use of key tools such as Kanban and hand flow devices, it is possible to schedule analysis occur in a controlled, repetitive way without large variations in workload or circumstances that result in sample backlogs causing delays at the manufacturing shop floor. Through the use of Kanbans to control the flow of samples, the oscillations can be avoided. Cellular layouts help eliminate waste and reduce turnaround times. The best arrangement shaped cellular arrangement, which puts sampling and some analysis instruments in close proximity in order to create a flow of samples around the processing area. Due to unconscious processing of spatial information through the right side of the brain, functions that pass left or counterclockwise more easily than those performed using clockwise motion. Therefore, optimal design processes that incorporate this movement appear to have a distinct advantage. It's been reported that sample travel has been reduced by 54% after implementation of a cellular or U-shaped arrangement. It's arranged in trays to provide adequate interruption to flow, help facilitate this flow arrangement. Rearranging the space into a system of cells often frees up workspace so that capacities can also be contemplated. Okay, so we've identified some of the cause laboratories to be problematic and generally ineffective. So if these are now crystallized in terms of lean operating principles, a basis is developed to create a meaningful forward strategy based upon a lean philosophy. To recap, some of the key points previously discussed, together with those following on below, we can see that all the structural elements are in place for the development of a lean strategy for the laboratory. One important point to always remember is that lean is always customer and value focused. And then if we address these points, we can build that value in the most effective way, which will put us on the right path for the generation of a lean laboratory operation. In review, some key points include: let's specify the areas of value. Let's use value stream mapping to accomplish this. Let's create a pull environment and a push environment. Let's level the load in sample mix. We eliminate waste. We manage performance. We lean the layout of the laboratory function. We reduce work in progress. We operate using planning tools. And where necessary, we use simulation modeling to enhance our operation. Let's look at specifying areas of value first. To produce a truly lean laboratory, you must identify every activity connected with the operation as either value added or non-value added. As previously stressed, doing this from the customer perspective will always yield a very clear and straightforward picture. One point to note: remember, this simple idea of waste is anything that the customer will not pay for, and value is anything that the customer will pay for. The goal then is to develop a snapshot for all the non-added value functions so that they can be eliminated, or in the worst case, reduced as much as possible. Value stream mapping. So it's important to identify the value stream through the current state VSIs. By following the principles previously discussed, this should now be easy and straightforward in terms of a process to complete. For the laboratory situation, the frequent bottleneck is connected with the release process, so this needs to be given particular focus as the mapping exercise is completed. Let's talk about creating pull. Make value flow and create pull in the system. The way forward is to produce a defined sequence of tests and to describe clear roles and responsibilities for the analysts and any support personnel involved. In doing this, you create a team that is pre-programmed to accept and progress samples as they arrive, and the level of predictability increases. The intent here is to provide a mechanism that assures that once an analysis is started on a given sample, it proceeds on to completion. This reduces the lead time of the process and produces concomitant increases in efficiency as a direct result. The pull in the system is generated by the customer demand for the analysis to complete the release of the matched product. Typically, the final element in the release process is associated with the rate limiting test samples. So all processes are often designed to be ready or completed to coincide with the time independent samples, either stability or potency, that may utilize a bioassay, for example. Leveling the load and sample mix. As previously mentioned, predictability is the goal of the lean laboratory because it results in the load leveling or smooth flow. The future state strategy needs to be to control the same/equivalent flow on a daily basis to permit load leveling and smooth flow to occur. Each area of the process may be adjusted for peak performance, and this will provide gains in overall productivity. So these benefits are profound, but if the sample workload is always going to vary, a mechanism is still going to be required which will control the analysis flow at the lab to present either a backlog or operate chaos to solve this problem. The first is a queuing mechanism. This is developed from knowledge and data generated from historical operations and is based upon accurate processing times for each particular analysis. Together with information about the best size for a batch to be processed, it allows the laboratory management to develop and model queuing, which specifies a must analysis start date and the acceptable efficient size of the sample analysis batch. In practice, the samples arrive daily in a centralized receiving area in the lab where labeled and numbered trays are arranged together with appropriate documentation. This is a highly visible arrangement which utilizes visual factory techniques to ensure that the work is according to a standardized work pattern and to a repeatable cadence or drumbeat known as a takt time. Once an effective queuing mechanism has been defined through analysis and assessment, the issue is to effectively execute the analysis to meet the goal of the standardized cadence for that process. Group analysis for a moment. Perhaps the easiest to implement is a grouped analysis, where similar or compatible analyses can be linked and performed together because of a logical connection. Another analysis tool is to use either a carousel, sometimes called a rhythm wheel mechanism, sophisticated and is employed for a regular repeating mode of action to affect lean benefits. Again, the basis of the mechanism is a repeating sequence defined by a known work pattern of incoming samples and a leveled customer delivery expectation. Having a constant delivery for the bulk of the incoming samples means that the various analyses can be appropriately spaced in time to stations, and this allows capacity to be fully utilized and staff resources to be maximized for operational efficiency. The real bonus here is that the samples will be tested, analyzed, reported, and decisions enacted upon based on that data on a regular, clockwise repeating basis that enhances the overability of the data. Both mechanisms work a principle that revolves around a defined starting date when the analysis is required to begin. If this does not happen, then the model will not operate effectively. Let's talk about standardized work. Standardized work is a contributing piece of the mechanism of success associated with the implementation of lean laboratory. Without a clean and mapped out program which details each individual sequence, the likelihood of success is limited. For each analysis performed by an analyst, a role needs to be defined so the individual understands what their contribution is to the operation and at what point it is necessary. Just like gears in a timepiece, if everything is synchronized properly, then the machine or the instrument will run as designed and to a desired level of proficiency. Such a big function about the elimination of waste. From the current state value stream map exercise, it's important to develop a punch list of low-hanging or fallen fruit opportunities to remove non-added value steps from the processing scheme. Remember that waste can include work in progress, scrap and rework of samples, excessive transport, wasted time with people, holding times that are unnecessary, and documentation, for example. In many laboratory applications, waste associated with waiting around often accounts for a significant percentage of the total non-added value component, which affects turnaround performance, for example. Some authorities in our field indicate that this may be as high as 50%. One way is to develop better interconnectedness and integration between adjacent and parallel activities. As mentioned earlier, workload leveling, the use of appropriate hijunker tools reduce problems due to high levels of work in progress, which will also positively impact turnaround times. To complete this, it's important to list all the assays being performed and the services performed, as well as special requests that frequently become part of a weekly routine. In completing this, one will generate a great repository of data from which to eliminate waste and to re-engineer the whole operation. Let's talk about managing performance. This has already been mentioned, but the only way to ensure that the changes being made are necessary to improve performance and reliability is to measure, trend, and report these results using good metrics. Essential to this process then is to identify and use key performance indicators. Tracking these key performance indicators daily and weekly will allow you to demonstrate that relative efficiencies of what you are doing and the overall efficiencies of the whole product are working properly. It will also help you determine how cost-effective the process runs and whether you are meeting your quality standards as attributes for the process. Typically then, this is done using a performance scorecard. This is a lot to cover. Implementing a lean laboratory is not an easy task, and many principles discussed earlier are very important to consider if you define your process operation. Through the implementation of these ideas, the new lean laboratory will be very quickly realized, and this will yield better resource utilization, resulting in improved competitiveness directly and indirectly. Lean the layout. It's important to focus on the routine operation of the laboratory in order to develop an optimum lean laboratory strategy. In particular, how the instruments are arranged relative to their use, where chemicals and solvents are stored and prepared, and where all the supplies are stored, as well as electronic aids like computers are stationed. These points will play a major role in determining state design for optimum flow, efficient use of space, and productivity improvements. As the layout is refined, it's important to remember to map the daily routines of the personnel, including analysts and helpers, the sample flow and the data flow. These elements will be key in the for a lean laboratory. Use of spaghetti diagrams are particularly helpful. They can be used to visually highlight the major areas of deficiency. Using these maps, it's easy to see the lack of coordination occurring in the laboratory, as evidenced, for example, by the long distance traveled by the analysts and the sample flow around the area. It's easy to understand then that this increases cycle times, preparation workup, and batching of samples. In the lean laboratory then, the emphasis is on the reduction of travel time by keeping the processing and analysis areas close together and by creating a logical flow that is both manageable and even by employing standard work practices. Experience demonstrates that between 40 and 70% of sample time may be reduced by employing a lean laboratory layout that minimize travel periods. The adoption of a cellular work pattern previously mentioned will provide a very significant reduction in the various waste components associated with the sample preparation. The GM layout is designed to focus all the key functions required to process a sample into a regular repeating unit. So what are the benefits? Let's highlight these. There's a reduction in sample movement, which speeds up processing and reduces non-value added travel time. There's a reduction in travel time spent by the analyst moving station to station to process the sample. There's preparation and processing of samples, which leads to fewer errors or malfunctions as a result of fewer hands involved. The fewer cooks in the kitchen concept is highlighted in this respect. Through the truncation of individual process steps, it is possible to simplify this and improve the flow with fewer errors and error-introducing handoff stages, as well as minimal batching of samples. Due to in smoother leveled flow, there is frequently a reduction in this turnaround time of up to 50%. Reduction in volatility can be exploited and converted into freeing up previously unavailable analysis capacity. This can translate into either increased productivity, a lower cost, or both. However, being part of an integrated value stream for the overall process, cadence of the laboratory function is best set to match the needs of the slowest point in the process, since moving any quicker will not add to the best outcome of the value stream. Hijunker devices. Through their repeating sequence process, they eliminate the need for customized planning tools by devising a process that can accommodate a mix of sample types. Even a buffer sequence can be introduced in a tool to prevent some functional variability without disrupting the balance level flow of the routine sequence of the analysis. Standardized work. Organizations have an integrated team of analysts that have managed time and function management. Given these realities, adoption of a lean standardized work pattern is particularly useful. Roles defined in role cards. What are these? Set out the actual tasks to be performed during each day for each analysis or support function person. Time is built in for morning and afternoon tasks with details about repeating sequences and time functions. Work in progress. This topic was reviewed earlier and focused on the use of Kanbans to control the flow of material being processed. This is frequently combined with the use of carousels or rhythm wheels to ensure that there is a steady flow, with analysis being conducted according to a highly regular cadence that ensures work in progress is kept to a minimum and analysis results are delivered to the customer within an acceptable operating range. Using this approach then, no analysis is started that cannot be delivered within its delivery date. Tools. This has much to do with planning. In order that flow does not sink into chaos, there are agreed rules that should be adhered to in order to deliver a successful pull flow condition. These should be defined by the cross-functional team members responsible for the development of the operating cell. And the overriding intent is that they should promote consistency and continuity in the cell's operation. 3 points should cover the following. 1. Only work that is processed should be released to the work cell for completion. 2. To avoid priority conflicts, work should be scheduled on a first in, first out or FIFO basis. 3. Work should not be processed outside the scope of the operating camera for that aspect of the process or function. 4. Material release should be avoided within the processing lead time. Otherwise, this might cause a buildup of work in progress and develop into a bottleneck or a backlog. 5. Scheduling the process cell at greater than 90% efficiency should be avoided at all costs. Otherwise, there will be insufficient flexibility to maintain a balanced flow when problems occur. Finally, let's just talk a little bit about simulation. This is just another very useful technique in the arsenal of the Prudence approach to developing a lean laboratory. The major advantage to this approach is that it allows the user to develop a test methodology in a virtual world and then without actually running a sample. Often, before a company will invest in a major overhaul to the system of work, they will want to be able to gain a comfort zone that the plan for changes will actually fit their situation. Also, by allowing a scenario to be developed in a virtual cost-free or limited cost environment, it's the implementation of the plan, do, check, act methodology created by Edward Deming to refine the basic operational structure prior to expending real resources and without disrupting current operations. So using implementation of simulation tools is a great way to build in flexibility into the lean laboratory strategy that can have a huge effect on the overall integrated operation of the QC function with the rest of the manufacturing plant operation.